Hello everybody, welcome back to Math 251. Hope you had a wonderful weekend. This is section 3.3's lecture video. Today, I think you're really going to like this lesson today. It's going to make derivatives a lot easier to find, so I think you're going to enjoy this lesson today. Our mathematician of the day is Maryam Mirzakhani, who was a Muslim woman who won the Fields Medal, which is like the Nobel Prize for math, in mathematics in 2016. She was the first woman to ever receive this prestigious award. Unfortunately, 2 years later, she died of breast cancer, very young, so that was very sad, but she accomplished a great deal in her short life. And did you know that the word 100 is derived from the Norse word hundrath, which actually means 120? So, whoops, that was kind of a little bit off there on the numbers, isn't it? It's kind of funny. All right, so today we will be discussing rules for differentiation. So far, we have been discussing derivatives in terms of the two limits with x approaches a and h approaches 0. We have been using those two definitions in order to find derivatives. And today we are going to learn some rules that make finding derivatives a little bit easier. So our first rule is called the constant in power rule, and it says the following. If c is a real number, so just a number, then the derivative of c is equal to 0. Now this makes sense. If we think about a graph of a constant function, say I have this, right? So this would be the line y equals c. The derivative is the slope, and this line does not have any slope. So that makes our derivative equal to 0. If n is a non-negative integer, then the derivative of x to the power of n is equal to n times x to the power of n minus 1. So this is a super handy rule that we will use for the rest of the term. The derivative of x to the power of n, where n is a non-negative integer for now. We'll learn more about non-integer exponents in a while. Then this derivative is n times x to the power of n minus 1. So with this in mind, I would like for you to pause this video real quick and try example 1 on your own using the theorem that we just learned. So go ahead and give example number 1 a try. All right, hopefully you've given number 1 a try. We want to find the derivative, first off, of x to the power of 9. Well, here, our n, our exponent, is equal to 9. So I take this n value and I put it in front. And then I have x times n minus 1, which will be 8. So I just move the exponent down in front of the x, and I subtract 1 from the exponent. Our next one is the derivative of x. Here, our n is 1, right? We have an invisible 1 in the exponent on this x. So when I move this 1 out in front, I just get 1x to the power of 0. But x to the power of 0 is just equal to 1. So this is just 1 times 1, or 1. So the derivative of x is equal to 1. Again, that makes sense because if we were to graph the line y equals x, its slope would be 1. And finally, we have the derivative with respect to x of 3 to the power of 7. Now, it's tempting here to say, oh, well, n must equal 7, and so I need to bring the 7 out in front and then subtract 1. However, 3 to the power of 7 is just a number. It's not anything having to do with x. It's just a constant. So by our first rule, if c is a real number, then its derivative is equal to 0. This derivative is just 0. All right. Next, we have another theorem that says if f is differentiable at x and c is a constant, then if I want to take the derivative of c times f of x, so something like 9, if I wanted to take the derivative of 9x to the power of 8, like we did, like we ended up with up here, I can bring this c out in front and multiply it by the derivative of f of x. Another way of writing this is c times f prime of x. So if I'm dealing with a constant multiple multiplied by a function, I can just bring that multiple out in front and differentiate my function as usual. So let's use this rule in order to find the derivatives of 6x to the power of 5 divided by 7 and 4/5 square root of x. So if I look at 6x to the power of 5 divided by 7, this is 6 over 7 times x to the power of 5 if we just bring our constant out. So if I take the derivative of 6/7 times x to the power of 5, according to this constant and multiple rule up here, I can bring this 6/7 out in front and then take the derivative of x to the power of 5. And according to the rule we just learned with our powers, this is 6/7 times, I bring our 5 out in front, and my new power is 4. So this is 30/7 x to the power of 4. That is the derivative here. Okay, if I look at 4/5 times the square root of x, I can't quite use my this theorem up here, the constant and power rules, because so far I only know n is a non-negative integer, and here 4/5 times the square root of x, well, I can rewrite this as 4/5 times x to the power of 1/2. Our power here is not an integer, so I can't quite use this yet. We'll get to that later. So instead, I am going to have to use my old limit definition. But we can bring this 4/5 out in front. So if I take the derivative of this, so taking derivative, gives me, I'm going to say 4/5 times the limit as h goes to 0. So I'm bringing that 4/5 out in front, and now I'm just taking the derivative of x to the power of 1/2, or square root of x. So if I, so remember, my definition is f of x plus h minus f of x over h. My f of x is square root of x. So this is 4/5 times the limit as h goes to 0. I have square root of x plus h. If I replace my x with an x plus h, minus square root of x, all of this over h. Now, in order to simplify this, I'm going to multiply the top and the bottom of this fraction by the conjugate of the top. So I'm going to multiply this by square root of x plus h plus square root of x over square root of x plus h plus square root of x. This gives me 4/5 times limit as h goes to 0. On the top, my square roots cancel and my two inner terms cancel. I'm left with x plus h minus x. And then on the bottom, I have h times square root x plus h plus square root of x. All right, well, my x's here cancel. And that means that I'm just left with h on top, so I can also cancel this h. And I am left with 4/5 limit as h goes to 0 of 1 over square root of x plus h plus square root of x. Now I can plug in 0 for h because it no longer makes my denominator equal to 0. So when I plug in h equals 0, I get 4/5 times 1 over, I end up with just a 2 root x on the bottom. And I can simplify this to 4 over 10 root x. So that is my derivative here. You could also simplify it to 2 over 5 root x. That's fine too. So we couldn't use the power rule on this problem because right now we only know the power rule for non-negative integers, but I could deal with the 4/5 by bringing it in front of the limit. So that was the point of that problem. All right, next we have what we call the sum rule, and it says the following: if f and g are differentiable, then the derivative of f of x plus g of x is equal to f prime of x plus g prime of x. And actually, this sum rule is true for any amount of terms. If I took the derivative of f plus g plus h plus I plus j, it would just be the derivative of each one of those terms added together. So for example, if I wanted to find the derivative of this guy, even though it's more than two terms, that's okay. The sum rule applies for as many terms as we have. So I'm going to take the derivative of each individual term and then add them together. So if I first take the derivative of negative 3x to the power of 6, this is equal to negative 3 times the derivative of x to the power of 6, or negative 3. Now what do I do here? I bring my 6 out in front, and I reduce my power by 1. So this gives me negative 18x to the power of 5. That was my first term. If I have the derivative with respect to x of the second term, 2x cubed, I can bring that 2 out in front. And now I bring the 3 down, reduce the power by 1. So this is 6x squared. The derivative of 10x, well, I bring my 10 out in front, constant multiple rule. And I found in my very first example that the derivative of x was equal to 1. So this is just 10 times 1, or 10. And finally, the derivative of negative 4, well, the derivative of any constant is equal to 0. So if I add all of these individual derivatives together, I get the derivative of our original function, h of x. So h prime of x is equal to negative 18x to the power of 5 plus 6x squared plus 10. So when I'm taking the derivative of a function that has lots of terms, I just take the derivative of each individual term and then add them together. All right. Next, we are going to learn the derivative of e to the power of x. Now, this is probably going to be your favorite derivative because, check it out. The function f of x is equal to e to the x is differentiable for all real numbers, and guess what the derivative is? The derivative of, e to the x is e to the x. Yes, this function is its own derivative. If you were to plug in e to the x into our definition of the limit as h goes to 0 of f of x plus h minus f of x over h, you would get this. It is true. Pretty amazing, right? So now we're going to use this to write an equation of the line tangent to the graph of f of x equals 2x minus x e to the x over 2 at the point 0, negative 1/2. Then find the points on the graph of f at which the tangent line is horizontal. Okay, so I first want to find the derivative of my function. Right, the line tangent, remember, the slope of the tangent line is simply equal to the derivative. So I first want to find the derivative of my function. So d dx of 2x minus 1/2 e to the x. Let's see, first I'm going to use the sum rule in order to split these into two parts. So this is equal to d dx of 2x plus d dx of negative 1/2 e to the x. So this was the sum rule. Next, I am going to bring out my constants. So I'm going to bring out this 2 and this negative 1/2, so I get 2 times the derivative with respect to x of x minus 1/2 d dx e to the power of x. So this was the constant multiple rule. And now I can just take these derivatives. So I know that, the derivative of x is just equal to 1. So this is 2 times 1 minus 1/2. And up here, I just learned that the derivative of e to the x is just e to the x. So my derivative is 2 minus 1/2 e to the x. So this is the slope of the tangent line at any point on our original graph. But I care about the particular point 0, negative 1/2. So in order to find the m tan at this point, I am going to plug in this point into my m sub tan to find the slope of the tangent line at that point. So we want slope at x equals 0. So my m sub tan will be 2 minus 1/2 e to the power of 0. Well, e to the power of 0 is just equal to 1. So I get 3/2. So the slope of the tangent line to this graph at the point 0, negative 1/2 is 3/2. And now I want to find the y-intercept. So I have y equals mx plus b. My y value is negative 1/2. My slope is 3/2. My b value, my x value is 0. So this makes b equal to 1/2, negative 1/2, excuse me. So my tangent line is y equals 3/2 x minus 1/2. Finally, we want to find the points on the graph of f at which the tangent line is horizontal. So if I were to, I don't know exactly what this graph looks like, but if I were to find, let's say my function looks like this. I want to find the points at which the tangent line is horizontal. So here, my tangent line is horizontal. Later on this term, we will learn that the tangent line is horizontal whenever my function has a local max or a local minimum value. In this graph that I just drew, our function has a local max. So that's just kind of a hint as what's to come. But I know that my tangent line has is horizontal when the slope is equal to 0. So when slope equals 0, we have a horizontal tangent line. Because a horizontal tangent line is something like the graph of y equals 2, and that does not have a slope. It is just a constant line. So therefore, we want to find where our slope equals 0. So I'm going to set my slope, which I found right here. This is my slope of my graph. I'm going to set this equal to 0. So I set 0 equals our slope, 2 minus 1/2 e to the power of x. If I add that 1/2 e to the power of x over, I get 2 equals 1/2 e to the power of x. Dividing both sides by 1/2 or multiplying by 2 gives me 4 equals e to the power of x. And now to solve for x, I'm going to take the natural log of both sides. and that gives me natural log of 4 equals x, or this is approximately 1.386. So this means that at the point x equals 1.386, I either have a local max or a local min, and that is where my tangent line is horizontal. So let's look at the graph of this function on Desmos. E to the 2x minus, we have y equals 2x minus 1/2 e to the power of x. So I see here that at this point, 1.386, this is my max. Here I have a local max. So if I were to draw my tangent line, it would have a slope of 0. All right, whoops. Next we have a function f of x equals 3x cubed plus 2x squared minus 4x plus 3. For what values of x does this function have a tangent line with a slope of 5? So this tangent line is a giveaway. Then I need to find the slope, the derivative. So that will be my first step. I'm going to find the derivative of f of x, and then I'm going to use that to find where my derivative, or my slope, is equal to 5. So the derivative of f of x is equal to the derivative of 3x cubed plus 2x squared minus 4x plus 3. I can use the sum rule in order to split this into parts. So this is the derivative of 3x cubed plus the derivative of 2x squared plus the derivative of negative 4x plus the derivative of 3. All right, well, the derivative of 3x to the power of cubed. Again, next I'm going to bring out my constants. So this is 3 times the derivative of x cubed plus 2 times the derivative of x squared minus 4 times the derivative of x. And we know that the derivative of 3 is 0. When you're taking derivatives like this, by the way, you don't have to go step by step like I'm doing. In fact, I won't do this for any lessons except for this one. But I do think that it's helpful to go step by step like this at first when we first learn this. That way we know where all of our numbers are coming from. All right, so now I can take the derivative. This is 3 times, bring that 3 down, x squared plus 2 times 2x to the invisible power of 1 minus 4 times 1, which is 9x squared plus 4x minus 4. So this is my derivative, or my slope, everywhere on our function f of x. And I want to know, for what values of x does this function have a tangent line, or a derivative, with a slope of 5? So this whole expression here represents my slope of my tangent line anywhere. So I'm setting 9x squared plus 4x minus 4. I want my slope to equal 5. Well, this looks like a quadratic function to me. I'm going to set it equal to 0. So I subtract 5 from both sides, and I get 9x squared plus 4x minus 9 equals 0. Unfortunately for us, this is not easily factorable, so I'm going to have to use my very favorite thing, the quadratic formula. So our a value is 9. That's this guy. Our b value is 4. And our c value is negative 9. So remember, The quadratic formula says x equals plus or minus b. Oh, sorry, what? B plus or minus the square root of b squared minus 4ac over 2a. If you need the quadratic formula on the exam, you will be given it. You won't be required to memorize this, though I imagine some of you do have this memorized. Okay, so now if I plug in, whoops, I missed a negative there, negative b plus or minus. So if I plug in these numbers now, I get negative 4 plus or minus 4 squared is 16 minus 4 times 9 times negative 9 over 18, which simplifies to negative 4 plus or minus. If I simplify under the radical, I get 340 over 18. And this is how I'm going to leave it. This is as simplified as I want to get. So at these 2 points, negative 4 plus the square root of 340 over 18 and negative 4 minus the square root of 340 over 18, I know that my tangent lines at those points of my original function has a slope of 5. So pretty cool. Next, we have the definition of higher order derivatives. So assuming that y equals f of x can be differentiated as often as necessary, the second derivative of f, we say f double prime of x is equal to the derivative of f prime of x. So if I want to find the second derivative, I just take the derivative of the derivative and so on and so forth. I can do this as many times as I want, as long as the derivatives exist. So for integers n greater than or equal to 1, I say the nth derivative of f. I notate it like this. So after a while, these prime symbols get a little bit hard to read. So we, after the second one, we write it like this. F to the power of n, this is the nth derivative, and I write the n in parentheses, of x is equal to the derivative of the nth minus 1 derivative. So this is saying the nth derivative of x, of f of x, is equal to the derivative of the n minus first derivative, which isn't a super satisfying definition. If any of you go on to take a course called linear algebra, you'll learn how to find these a little bit more straightforward. But for now, we just have to keep taking derivatives. All right, so we want to find the third derivative of these two functions. F of x equals x to the power 4 minus 7x cubed minus 6x, and gx equals 4x plus 5e to the x. So I first have to take my first and my second derivative in order to find the third derivative. So f of x equals x to the power 4 minus 7x cubed minus 6x. F prime of x, this will be equal to 4x cubed minus 7 times 3x squared minus 6, or 4x cubed minus 21x squared minus 6. That is my first derivative. To find the second derivative, I take the derivative of this guy. So f double prime of x is equal to 4 times 3x squared minus 21 times x, and the derivative of negative 6 is 0. So this is 12x squared minus 21x. Oh, whoops, I missed a 2, didn't I? 2x. 21 times 2x. Forgot about that, this power 2. So that means that this is 42x. Okay, so that is my second derivative. And now I need to find the third derivative. So f triple prime of x is just the derivative of the second derivative. So 12 times 2x minus 42 times 1, which is 24x minus 42. That is the third derivative. Later on, we will learn some applications of the second derivative in terms of some physical applications. So that's why this process is useful. And then we have our other function, g of x. So g of x equals 4x plus 5e to the x. I take the first derivative, and I get 4 times 1 plus 5 times e to the x. Remember, the derivative of e to the x is just e to the x, which is just 4 plus 5 e to the x. Now I take the derivative of this to get g double prime. G double prime of x is equal to the derivative of 4 plus 5 times the derivative of e to the x. Well, the derivative of 4 is 0, plus 5 e to the x. That makes g triple prime of x, or if you want to write it as g parenthesis 3x, that is just 5 times the derivative of e to the x, which is 5e to the x. So I think you guys will like taking derivatives of stuff with e to the power of x because it's generally pretty simple. All right, so we covered a lot of rules and materials today. You will get a lot of practice using all of these rules throughout the term. So let me know if you have questions on this lesson. I hope to see you in our Zoom meeting at 9 a.m. and 3 p.m. Pacific time. So yeah, I will see you later.